Welcome to Industrial PLC Applications. This video is a part of the Deeper Look series and will focus on the correct application and deeper understanding of the XIC and XIO instructions. There are a lot of electricians who find the above logic confusing, especially if DI_09 is a normally closed device. Perhaps the best way to explain this is to go totally retro. There, that's better. No, wait. That's not retro enough. Let's go back even further. Perfect. Good old-fashioned CRT display. Now, besides the color, you might notice there's a few visual differences. Like, for one, the rails are not connected. And for two, the lines between the contacts and coils are dashes. Now, notwithstanding that they had to use ASCII, which is typewriter to computer keyboard code, to write the logic, these visual differences also happen to serve to remind us of how the PLC works. The rails are not connected because each rung is a step in a list of executable lines of code. At least, that's how the PLC's CPU is going to interpret them. It's like saying, look at the set of instructions and resolve what the instructions say. This first instruction doesn't look like an instruction, but it is. It says, this is a new line of code to examine and logic to resolve. Take your latest input scan and apply that information to any instruction that follows until you are told to move to the next line of code. This instruction tells the CPU to go to the memory location listed. Yes, inputs and outputs are, at least to the CPU, memory locations, and determine if there is a 1 or a 0. With I/O, the presence of a voltage sets a 1, the absence of a voltage sets a 0. Then, continue resolving the logic. This instruction states, if the location has a 1, it satisfies this instruction, so it is true. If the variable location has a 0, it does not satisfy this instruction, so it is false. However, this instruction also tells the CPU to examine a stored variable. But here, if the value is 0, then the instruction is satisfied, so it's true. If the value is 1, then the instruction is not satisfied, so it is false. This may look like a line made with dashes, but it's actually an instruction. If not an instruction, why didn't the software writers back in the day just use a spacebar or underscore? Because the dashed lines indicates make a connection. This instruction means make a connection between the last instruction and the next instruction in series on the rung. Remember, a PLC doesn't do any wiring. That's our job. But it can make logical connections, and thousands of them with no additional wiring needed. It can connect devices and logic that would be physically impossible or impractical to do in the real world. Here it is making the connection between the logical result of our contact instruction and the resulting outgoing coil instruction. This instruction tells the CPU to write a 1 or a 0 at the memory location listed for every scan. If the logic up to this point is true, then write a 1 in the memory location. If the logic up to this point is false, then write a 0 in the memory location. These instructions are followed for every single scan. For example, the first scan instruction is 0. The logic says, write a 0 to the output. Second scan, the instruction is 0. The logic says, 0, rewrite a 0. The third scan, the instruction is 1. The logic writes a 1 to the output. Every rung is overwritten on every scan. This last instruction tells the CPU that the rung is logically complete. Move on to the next rung of logic. Because most troubleshooting experiences are trying to determine why something didn't happen, you often start with the failed output. From there, you are looking for what is missing. So let's start with the results of a rung of logic, the output. The OTE instruction, output energize. We're going to start with the result rather than the logic. With most PLCs, you can't have a rung without an output. It's a logical dead short. But you can have a rung with an output and no instructions ahead of it. Furthermore, it's important to remember that the output is the last thing to be set in the PLC's operational scan and execution. And you, the programmer, determine what to do with the logic leading to the final execution of the logic. In other words, at the end of the rung, what do you want the PLC to do? This instruction is called OTE, output energize, or a direct coil. It is the simplest and most common output instruction. Turn something on or off. If the logic before it is true, then write a 1 at the memory location attached to this instruction. If the logic before it is false, then write a 0 at the memory location. Now that we have at least one output instruction that concludes the logic, we can begin to look at the instructions ahead of the output. Again, let's start with the simplest and most common, or the most misunderstood one. And they happen to be the same thing. This instruction is often misunderstood simply because it looks like a set of contacts to an electrician. And that wasn't by accident or convenience. It was for practical reasons. Electricians were not coders when PLCs first arrived in the 1960s, and yet they had to quickly recognize what the logic was doing. In fact, if it were up to programmers, this is how the logic would appear. Just code. Not exactly easy to understand and visually confusing, even if you knew what it was saying. And since the PLC doesn't care which type of device is on or off, well, a simple contact was chosen. This instruction tells the CPU to examine the state of a named variable's single binary digit. The variable could be the memory location assigned for a real-world input, or the operational status of an output, or the value of an internal memory location. If the CPU finds the value of the location is 1, either by being overwritten by another instruction, or a voltage being detected at an input terminal, or a 1 being written into a force table, which we'll cover later, then it remembers a 1 for the rest of the logic. If the CPU finds the value of the variable is 0, then it remembers a 0 is to be applied to all locations with that variable identification. Now, focusing on the prints, this works fine for a normally open device connected to an input terminal. As real current flows to a switch, it can flow to the PLC. It just depends on the state of the switch itself. So returning to our example logic, if the variable in the first rung is false and has no voltage, or 0, then make a connection to the next instruction, the OTE, and resolve it, using the stored information to determine the output's outcome. In this case, the output would be turned off, and a 0 would be written to that memory location. I realize I've drawn a line that would not appear on a PC's screen. This is because the screen you view is processed through human-centric software, and we need a visible clue as to what's happening. The output instruction to us is a coil, but to the PLC it is a write instruction, and in this case it is writing a 0. When the normally open switch is closed, current flows to the terminal screw, so the PLC places a 1 in a memory location. But now that you have that, how do you want the PLC to interpret that voltage being detected, that 1 placed in the memory location? Remember, this instruction says if you see a 1, then remember that 1 and carry on. Execute if charged or examine if closed. So returning to our logic, if the memory location is true, that is to say it has a voltage or equals 1, then make a connection to the next instruction, the OTE, and execute that instruction. Since our XIC is charged, the CPU writes a 1 at that memory location, and since that satisfies the instruction, a connection is made to the OTE, which, in turn, overwrites its assigned variable to a 1. This overwriting is considered to be a destructive action. The XIO instruction tells the CPU to look for a 0 at a variable's memory location, or an absence of voltage at an input terminal screw. And if either situation is found, then the instruction has been satisfied and is true. Therefore, continue executing the logic. If the CPU finds that the variable has a 1 or an applied voltage, then the instruction is not satisfied, it's false, and therefore the CPU will apply that to the logic, which in this case turns the output off. Now let's take a look at what happens when we are dealing with a normally closed device like a stop push button. When a normally closed input has power applied, it behaves like a dead short. That is, it passes the current directly to the PLC input terminal. Therefore, there is a voltage at the terminal, and the PLC's input memory location will have a 1. When the rung is scanned, the XIC instruction is satisfied, and the CPU connects with the output and turns it on by writing a 1 to the output variable. Conversely, since a normally closed input passes the current directly to the PLC input terminal, the PLC's input memory location will be 1. When the rung is scanned, the XIO instruction is not satisfied, and so the CPU resolves that the logic is false. It then writes a 0 to the output variable. With these instructions, focus on the output and not the value or state of an input variable. Rather, focus on what you want the rung to do and in what state do you need a variable to be in order to produce the results you want. With that in mind, there are situations when the opposite state can or needs to be used in order for the logic to work. For example, an XIO is used in interlocking, and an XIC that's turned off is often used to make false a rung. When you put an XIC and an XIO of the same variable in series, they will negate each other, which will falsify a rung or a branch. Always remember when it comes to these two instructions, these are called contacts, but they are not contacts in the typical manner. These are instructions because they instruct the PLC's CPU to take particular actions. If you know the mnemonic, XIC is execute if charged, or XIO execute if off.